Hi students, we are going to review in-class exercises 4 and 5 of electrochemistry in this video. For question 1 of in-class exercise 4, we have strontium metal being abstracted from molten strontium bromide via electrolysis. Do take note of the keyword molten here, because molten here means that strontium bromide is in the liquid phase. It is not in the aqueous phase. Yeah, because if you think about it incorrectly, then you will predict the wrong product at the anodes and the cathodes. So in molten strontium bromide, there are only two ions. One is strontium 2 plus in the liquid phase. The other one is bromide in the liquid phase. Okay, so over at the graphite anodes, I expect bromide to be oxidized. Okay, so it's in the liquid phase. Bromide to be oxidized to give us bromine. At such a high temperature, if you do check up, the melting points of strontium bromide is about 640 plus degrees Celsius. So this whole setup is likely to occur at around 650 to 680 degrees Celsius. So at that temperature, I expect bromine to exist as a gas. So it will be produced as a gas accompanied by 2 electrons. Okay, so plus 2 electrons. And then at the cathodes, I expect strontium to be reduced, okay, by coming in contact with the cathodes. So it will be reduced to strontium metal, okay, but at such a high temperature, strontium metal is likely to be a liquid as well. So I'm going to put in the state symbols as liquids. Okay, then for part B, the question asks, suggest why an atmosphere of argon is used around the cathodes. So you notice that over at the cathodes here, it is surrounded by an atmosphere of argon. I think we can easily reason this out, because strontium being a group 2 metal, its 2 valence electrons is relatively loosely held. And given the fact that strontium is quite low in the in group 2, which means it's just below calcium, but below strontium will be barium, so they are likely to be quite reactive in the presence of oxygen. Yeah, so if you don't want the metal to react upon its formation, then it is better to keep it under inert conditions. Yeah, so the inert condition we can think of will be argon. Yeah, I mean, argon being an inert gas, it is unlikely to react with the strontium freshly produced. Yeah, so what you can easily write out as an answer would be strontium being a highly reactive metal. It can easily react with oxygen to give us strontium oxide. Okay, so that is one part of the answer you can focus on. You can say that an atmosphere of argons instead of the normal atmosphere we are living in will prevent the oxidation of the newly produced strontium to give us strontium oxide. If you wish to, you can also highlight that strontium is likely to react with the water vapor in the air, and in the process we might end up with strontium hydroxide on the surface. Okay, so these are two possible byproducts or side products if it is produced in atmospheric condition. Okay, then for part C, we were told that a current of 5 ampere was passed through molten strontium bromide for 60 minutes. So we are required to calculate the coulombs passed through. So we can do that quite easily. So if you recall the lectures on electrochem, you will introduce that the charge transfer, which is Q, is equals to the product of the currents multiplied by the time. Okay, we are given the current, so that's 5.0. We are given the time to be 60 minutes, so 1 minute is 60 seconds, so we're going to multiply 60 by 60. Okay, so if we punch the calculator, we'll get about 18,000 coulombs. Okay, so that's for part 1. Okay, so this is part 1. And then for part 2, the mass of strontium metal form. Okay, so we know that the charge transfer is also equals to the number of moles of electron transfer multiplied by Faraday. Okay, so if you check out your data booklets, Faraday is 96,500. Yep, so therefore the number of moles of electron transfer is equals to Q, which we have gotten from part 1, 18,000 Okay, so divide by the Faraday constant, that's 96,500, and then we'll be able to get 0.187 moles. Okay, this is the number of moles of electron transferred. Yeah, so you need to be very clear what you are calculating. So over here we are calculating the number of moles of electron transferred, yeah, which is 0.187 moles. From here, we cannot straight away calculate the mass of strontium metal form, because earlier on we know that the stoichiometric ratio between strontium metal and electrons is 2:1. Yeah, so in order to calculate the number of moles of strontium metal, we need to divide this value by 2. Okay, so therefore from here we can calculate the mass of strontium produced. Okay, so that will be equals to 0.187 divided by 2, multiplied by the relative atomic mass of strontium, that will be 87.6. Okay, yeah, then from here we will be able to get 8.17 grams. Okay, so do punch your calculator and double check whether this value is correct. Okay, then we'll move on to part D. We will ask, explain why aqueous strontium bromide cannot be used to extract strontium by electrolysis. Yeah, so to answer this, we have to take a peek at the standard reduction potential values. Okay, so if you take a look at the standard reduction potential value, you notice that the reduction potential value of strontium is not found. Yeah, so does that mean that we can't do this question? No, we can use the value of calcium and barium as an approximation. We are given calcium to calcium, that's minus 2.87 volts. We are also given barium to barium, that's negative 2.90 volts. So that means that I would expect the reduction potential of strontium to strontium to be between minus 2.87 to minus 2.9. Okay, so that is a very negative reduction potential. And what are we comparing it with? We are comparing it with the standard reduction potential of water H2. Yeah, so this is the one we are comparing with. So you notice that the standard reduction potential of strontium to strontium is likely to be more negative than that of water H2. Yeah, so because of that, I expect water to be reduced to hydrogen gas, okay, or to be preferentially reduced to hydrogen gas at the cathodes, rather than strontium metal being reduced at the cathodes. Okay, yeah, so that should form the bulk of your answer over here. If you are not sure what to write, I think the first thing you need to highlight is that the standard reduction potential of strontium to strontium is likely, my apologies for the pen, okay, so it's likely to be between negative 2.87 volts to negative 2.90 volts, which is significantly more negative than that of the reduction potential of water H2. Okay, yeah, so because of that, that means that H2O is preferentially reduced at the cathode instead of strontium 2+. Okay, so therefore hydrogen gas will be produced. I mean, if you want to continue writing, you can. Hydrogen gas will be produced instead of strontium. Okay, so I hope that will be that is how you should draft your answer. Do take note, as I mentioned many times, whatever I've written here is just a very rough way, a very skimpy way of drafting the answer. I have showcased out the thought process. So if you are copying down the answer as it is, I don't think you should do that. These are the main ideas, so you should catch some of the main ideas and then craft out the answer on your own. Okay, for question 2a, right, over here we have sodium chlorate. Is an important industrial chemical. So many thousands of tons, okay, is being produced or is being used each year in the manufacture of chlorine dioxide bleach for the paper industry. It is made commercially by the electrolysis of brine in a cell with no diaphragm, so that the solution at the anode and cathode mix up. Okay, so the details, I don't think you need to go into that because the nature of the question does not require all these details. But what is really important for you guys would be the two equations over here, because for the first equation, it involved the reduction of chlorides to give us, or rather, sorry, it involved the oxidation of chlorides to give us chlorates. Okay, so it's written out in a relatively weird manner. So usually we'll write the 6 electrons on the right hand side. That's why earlier on I get a little bit confused. Yeah, so I'm sure some of you might get confused as well, and this is not uncommon. So when you are doing question, sometimes you just need to make sure that you read the information accurately and correctly. Yeah, so do not rush through question in exams. Okay, so first of all, we are required to calculate the current needed to produce 1 ton. You are told how much is 1 ton. That's 10 to the power 6 grams of sodium chlorate per day. You were told that 1 day, that's 24 hours. I mean, that's obvious. So therefore, the amounts of sodium chlorate, NaClO3. Okay, remember to include the Na. Some of you did not include the Na. Okay, 1 times 10 to the power 6. Okay, and then I divide this by 23.0 plus 35.5 plus oxygen is 16 times 3. Okay, if I take out the calculator and punch, I should be able to get 9.390 times 10 to the power of 3 moles. Okay, so that's quite a bit. And then if I produce this amount, so that will be equivalent to ClO3 minus, and then the stoichiometric ratio between chlorate and the electron transfer is 1:6. So therefore, number of moles of electron transferred, okay, will be equals to 9.390 times 10 to the power 3 multiplied by 6, and then I take out the calculator and punch the values. 5.634 times 10 to the power 4 moles. Okay, so since we know that Q is equals to the number of moles of electron transferred multiplied by Faraday, then we will, and this is also equals to currents multiplied by the time. We can therefore calculate the currents by equating the number of moles of electron transferred, that is 5.634 times 10 to the power 4 multiplied by the Faraday constant, that's 96,500, divide by the time. So the time is 24 hours. So in 24 hours, 1 hour we have 60 minutes, 1 minute we have 60 seconds. Okay, and then once I punch the calculator, I will get a very weird value. It's a super huge value. I'm going to get like 6.29 times 10 to the power 4 ampere. That's a huge number. Okay, but for the industry, that might be viable. I'm not sure. Okay, yeah, so that's the number you're going to get. If you're doubting your answer, you can double check and see whether you have gone wrong anywhere. Okay, and then for part 2, calculate the volume of hydrogens measured at RTP that is also produced. Okay, so over here in the process, 3 equivalent of hydrogen gas is being produced. Okay, so that means that the ratio will be 1 equivalent of ClO3 minus to 3 equivalents of hydrogen gas. Yeah, so one way you can do it is simply just multiply this value by 3, or you can simply just divide this value by 2. It's up to you how you want to do it. Okay, you can just straight away calculate. So volume of hydrogen produced is equals to I choose to do it this way, 9.390 times 10 to the power of 3 multiplied by 3. Okay, and then multiply by 24, since I'm told that I'm supposed to calculate the volume at room temperature. Okay, so that will give me 6.76 times 10 to the power of 5 dm cubed. Okay, yep. Right, so we are done with in-class exercise 4.